Hello, in this tutorial, I'm going to design a ring oscillator Cadence Virtuoso with a 45 nanometer technology. So before going to design, I'm going to follow this paper. Here the author describe how to design a ring oscillator. We all know that if we take an inverter and if we cascade those odd number of inverter and if we make a forward feedback path with the first and last inverter, then it will be works like a oscillator. So how to get the frequency, desired frequency on this oscillator? So to get the oscillation frequency, I have to calculate the propagation delay for high to low and low to high. After sum those propagation delay, then I have to multiply it with n number of stages. Must be the n is odd number of stages. Then if I divide it by it 1, then we get the design frequency. So there are so many theoretical explanation. I'm not going to this part, but I'm going to the design part. So first of all, I have to design an inverter. I already designed an inverter schematic, and this is for the input A, and I put here 0 volt and then 1.8 volt, and then the period is 20 nanosecond and the pulse width is 10 nanosecond. After that, I have to launch the ADL. Here you can see that I give here the variable width because I want to vary those length and width for sizing the inverter. So also for the CMOS, see there I set a variable ln wn that launch the ADL. Copy from the cell view. I'm going to transient analysis. If it is at 20 nanosecond, then if I show the 5 cycle, then 100 nano. For the DC output response, then I have to select a component parameter. Let's say the length CMOS length is 45 nanometer. PMOS length also 45 nanometer. WN, let's give it to 145 nanometer. And if I take arbitrary value, then 80 nanometer. Okay. First, then I have to run the DC analysis to show the switching threshold voltage. I have to plot. This is because I'm not giving it power in this device. If I find the switching threshold, then press V. If it is a 1.8, so it must be for a same propagation delay for the NMOS and PMOS. It should be VDD by 2. That's why 0.998 millivolt. You can see here, this point is not 900 millivolt. So I have to set the point here. How can I do that? So I have to increase the PMOS width, because we all know that the mobility of the PMOS is lesser than the NMOS. So I have to increase the PMOS width. So that's why I'm going to the parametric analysis. WFIT. Oh, it should be 5 steps. Okay. So the point in between the racing width 180 nanometer and the 260 nanometer. This point is in between these two width. So let's use the set of switching threshold. Give a name, open close function, then where the close. The threshold voltage is VDD by 2 or 0.9. Apply. Get expression. So in x-axis here is the PMOS width and y-axis the voltage range. So I have to find which lane the voltage is 900 millivolt. So first is horizontal line and 0.9, it's 900 millivolt. So the PMOS width should be 210 nanometer. If the PMOS width is 210 nanometer, then the switching threshold will be the VDD by 2. So I find the PMOS width, which is 210. So I'm going to here set the PMOS value 10 nanometer and apply. Okay, then if I plot the out now, so you can see here the switching threshold is 900 millivolt divided by 2. So we size the NMOS to close window. So if I show the transient response, this is input and this is the output. If the input is high, the output is low. From the transient response, I have to find the propagation delay. Propagation delay, first select the wave, and then find a function which is called delay. Signal 1 is A, the input, and signal 2 is the output. And this threshold is 0.9, which is VDD by 2. And then if I find the first high to low, then rising and then falling, it is the TPHL, high to low. Then click apply. So this is the TPHL, and copy the result. The TPHL value, after that low to high, falling to rising, line. Okay, I get the TPHL and TP low to high. Then I have to add those two values. The should 1 divided by n into TPHL plus TPLH. And then I have to put the stage. If I set the 11 stage so I get 3 point. By the way, let's check. Oh, here I have to add those two propagation delay. Then I get the oscillation peak frequency, which is approximately 9 gigahertz, 8.7, approximately 9 gigahertz. After around the simulation, it will be it will be larger than the calculated value, 9 gigahertz. Then what is WP, which I get from the parametric simulation. WP is 210 nanometer, and the WN is 45 nanometer. Okay, then let's design the oscillator. Here I already draw the schematic. You can see here is the 11 stage of inverter, and then I have make a feedback path from the first stage to last stage, and here is the two voltage source, which one for the VDD and one for the BSS. Here I put the 0 volt for the BSS, and here I put the VDD for 1.8 volt. And then I have to launch the ADL. After run the ADL, then I have to copy the variable from the cell view and set the variable, which is 45 nanometer, was length also 45 nanometer. Then WN is 145 nano, and WV, which I get from the parametric analysis, 210 nano. After that, I have to set the transient response. If it is a gigahertz, so I have to make it nano or pico. Then simulation, make it initially 0. So here I get the oscillation frequency. So if I make it 1 nano, so this is basically the oscillation frequency. If I calculate the frequency, then I have to use the calculator. And then put frequency, and then we will click it in wave. Okay. To apply, you can see here we get the approximately 10.7 gigahertz. When we calculate it, then we approximate the frequencies 8.7 gigahertz. So this is the difference between the calculation and the simulated frequency, but it's too much closer what we approximate and what we get. So to get the appropriate frequency 8 gigahertz, then there is a process that then we have to add some inverter. Also, here is another technique that if you vary the W by W and L, or Wn and Wp, then the delay will be increase. And because as we know, the oxide capacitance depends on the W and L. So if you increase the W, then it increase the capacitance and also it increase the delay. And if the delay increases, then also it changes the frequency. Like if I make it 500 nano, let's see what will the change. Let's calculate. Now the frequency is 8.63 gigahertz. So our calculation is 8.75 and we get the 8.63 gigahertz. In this way, you can design a ring oscillator. So thank you for watching this video.